If we have ordinal or not normally distributed data, ANOVA might produce a wrong result. That's why we need Kruskal-Wallis test. Kruskal-Wallis test you see on the screen right now answers two questions: whether at least one group is different from other groups, and between which groups exactly this difference is. So let's learn how to get and interpret all these results. For that, we'll take 50 individuals from 5 different educational backgrounds, compare their salaries, and find out where the education matters by conducting Kruskal-Wallis test. And the best way to compute Kruskal-Wallis test, in my opinion, is the ggbetweenstats function from ggstatsplot package, which needs only 4 arguments. First, our data D, with x-axis having grouping variable education and y-axis having salaries. Then, since our data is not normally distributed or ordinal, we'll choose a nonparametric type of statistical approach, and ggbetweenstats automatically takes Kruskal-Wallis test if number of groups in education is higher than 2. Such simple command results in this statistically rich and publication-ready plot. Now let's interpret the results. Chi-squared test statistics and the degrees of freedom were previously used to manually calculate p-value. But nowadays, since p-values are always calculated by software, we can safely ignore it. Our very small p-value shows a very strong evidence against the null hypothesis that salaries across all groups are similar, in favor of the alternative hypothesis that salaries of at least one group differ. However, there are 2 problems with the p-value. First, a significant p-value only tells you that a difference between groups definitely exists and did not happen just by chance. But a p-value cannot tell how large this difference is. Fortunately, ggbetweenstats provides partial epsilon squared with 95% confidence intervals as the measure of the effect size for Kruskal-Wallis test. Our effect size of 0.36 indicates that the effect of education on salaries is large. For example, a person who studied a lot earns approximately twice as much as the person who did not even finish his high school. So the effect size makes total sense to me. A second problem p-value has is that it tells us that a difference between groups exists, but it doesn't show between which groups exactly. That's why we need to compare every education category to every other education category pairwisely. And luckily for us, ggbetweenstats automatically knows that we need done pairwise tests for a significant Kruskal-Wallis, conducts those tests, displays p-values, and even corrects these p-values for multiple comparisons without any additional code. How cool is that? However, if we want to, we can easily customize the results by using either additional code within the function or code from ggplot2 package outside of it. For example, you can manipulate the data, you can display outliers, you can change Holm correction for multiple comparisons to a more famous Bonferroni correction. But I wouldn't recommend that because Bonferroni correction is too conservative and we might miss an important discovery. Then, if you want to display not only significant but all comparisons or change the appearance of your plot, you can easily do that and much more. Just write a question mark in front of ggbetweenstats and explore this interesting function. But what is even more interesting is the fact that the 2-group case of Kruskal-Wallis test is identical to the Wilcoxon rank sum test, because they both compare rank sums of groups but not medians, although medians are often displayed. In fact, the groups can be significantly different even when medians are identical. And if you want to learn more about this, check out this video.